Hello everybody, this is Professor Jing. This week we'll be discussing simple linear regression. Here are the learning objectives. After this class, the student should be able to calculate the correlation between two variables, be able to discuss the differences between correlation and regression, as well as be able to explain the method of ordinary least square. And also, the student will be able to check the assumptions for simple linear regression and interpret the result of simple linear regression, and especially be able to interpret the coefficient of determination. A correlation or simple linear regression analysis can determine if two numerical variables are significantly linearly related. A correlation analysis provides information on the strength and direction of linear relationship between two variables. First, let's see an example of correlation. Suppose I would like to know if weight is associated with systolic blood pressure. I collect weight and systolic blood pressure from 10 people. Suppose the data are plotted and the diagram looks like this. To determine how strong these two quantitative variables are linearly related, we can look at the correlation coefficient. This is a number between -1 and +1 that expresses how tightly the data fit around the imaginary straight line through the scattered dots. From the correlation coefficient Pearson R, we can learn that whether the relation is positive or negative. In this case, the systolic blood pressure increases with increasing weight. Pearson's R should be positive. We can also see that the correlation is relatively strong, which R is equal to 0.74. Of course, this means that it might be a better idea to control your weight, since weight is positively associated with systolic blood pressure. It will be useful to describe the relationship more specifically and be able to predict an exact systolic blood pressure based on an individual's weight. But the correlation doesn't give that information. This is why we use linear regression. It describes the relation mathematically through a regression equation and gives blood pressure prediction for each weight of individuals. This allows us to do a couple of interesting things. We can use inferential statistics to test if the equation is likely to be an accurate description of the relation in the population. We can also see how closely the prediction approximates the observed data points. In other words, how good our predictions are. We can use the regression equation to identify outliers, the data point that deviates strongly from the rest. And finally, we can generate predictions for new cases. For example, to estimate an individual's systolic pressure based on his or her weight. In scatter plot, the pattern of data is indicative of the type of relation between your two variables, positive, negative, or no relationship. Here is an example of a positive relationship. You can see that the number of hours spent on study is positively associated with final grades in the course. In other words, the more time you spend, the higher grades you get. Here is an example of negative relationship between age of car and their reliability. This diagram shows no relationship between weight and pulse rate. There is no clear pattern. Those dots are randomly distributed in the diagram. The Pearson correlation coefficient R measures the degree of relation between two quantitative variables. The sign of R corresponding to the direction of relationship. If R is positive, then as one variable increases, the other variable tend to increase. If R is negative, then as one variable increases, the other tend to decrease. A perfect linear relationship when R is equal to -1 or +1. It means that one of the variable can be perfectly explained by a linear function of the other. The Pearson correlation coefficient can take on values between -1 and 1. The further away R from the zero, the stronger linear relationship between the two variables. Here is the rule of thumb that can guide your interpretation of R. Typically, we look for correlation coefficient larger than 0.5, as it is the indication of either moderate or high correlation. Here is the formula for simple correlation coefficient R. Let's look at examples so that you will have better understanding of this formula. We have a sample of 6 children. The data about their age in years and weights in kilograms was reported as shown in the following table. We want to find the correlation between age and weight. These two variables are quantitative variables. One variable, age, is called the independent and denoted as X variable, and the other, weight, is called dependent and denoted as Y variables. In order to find the relation between age and weight, we need to compute the simple correlation coefficient using the following formula shown in the previous slide. We have x times y, x squared, and y squared, and the summation of x, y, xy, x squared, and y squared. Now we have everything needed. Apply the formula. We have R equal to 0.759, which shows a high positive correlation between age and weight. It is time to exercise your knowledge on correlation. Remember, a steeper slope suggests a higher correlation. Which of the following graph has a correlation coefficient of -0.95? Which of the following graph has a correlation coefficient of -0.9? Which of the following graphs has a correlation coefficient of 0.49? And which of the following graphs has a correlation of 0.93? A simple linear regression analysis estimates parameters in a linear equation that can be used to predict values of one variable based on the other. Typically, we use an independent variable x to predict outcome or dependent variable of y. The result of simple linear regression can tell you how the values in y change as a function of changes in value of x. If we use age to predict weight, from the result of simple linear regression, we can know that how much weight an individual gains with a year increase in age. Both relation and simple linear regression analysis can determine if two numeric variables are significantly linear related. However, a correlation describes the strength of a linear relationship between two variables, while regression tells us how to draw the straight line described by the correlation. Linear regression consists of finding the best fitting straight line through the data points. The best fitting line is called a regression line. The white diagonal line in the graph is the regression line and consists of predicted score on systolic blood pressure for each possible value of weight. How to get the best fit line? In simple linear regression, we assume that the relation between the predictor and the response variable is linear. So first of all, the line must be straight. Second, we get the best prediction from the line that produces predicted score that lies as close as possible to the observed score. So we need to find a straight line that minimizes the distance between observed and predicted score for all cases in our sample. The difference between the observed and predicted score for each case is called a residual or predicted error. It is expressed as y sub I minus y hat sub I for case I. For the best fit line, we use the method of ordinary least squares. We take the residual y sub I minus y hat sub I, we square those residual and we add them up. We square because otherwise the positive residual, where the observation lays above the line, will cancel out the negative residual, where the observations lays below the line. The regression line makes the sum of the square of the residuals smaller than any other lines. Regression line is described by the regression equation. It gives predict response variable score for each value of the predictor. The equation is y hat sub I equal to a plus b times x sub I. Y hat sub I is the predicted score on the response variable y, systolic blood pressure, for case I, giving their value x sub I on the predictor x weight. The predicted score is determined by the intercept a and the regression coefficient or slope b. The intercept a is equal to the value of y when the x equal to 0, where it crosses the y-axis. It determines where the line is spaced. The regression coefficient b determines the slope of the line. It determines whether it goes up or down and how steep it climbs or falls. It tells us by how much the systolic blood pressure will increase if the weight increased by 1 unit. So in this case, 1 kilogram. The good thing is that you don't need to calculate B by hand, as SPSS reports the coefficient of linear regression for you. Again, the regression line is expressed as y hat equal to a plus b times x, where a is the intercept, b is the slope. This line tells us that 1 unit change in x will lead to b units change in y. Simple linear regression was performed to examine the relationship between number of hours spent studying and final grades in the course. The result shows predicted final grade is equal to 59.95 plus 3.17 times the number of hours you study per week. Let's say someone spent an hour of studying per week. Then his final grade is predicted as 59.95. If Alice spent 1 hour studying per week, her final grade is predicted as 59.95 plus 3.17 times 1, which is equal to 63.12. If Kim spends 10 hours studying per week, her grade is predicted to be 55.95 plus 3.17 times 10, which is equal to 87.65. You can see that with this regression analysis, we can predict a student's final grade based on the number of hours he or she spent on studying per week. Once we obtain the regression line, we can use to give a summary of the relationship between exploratory and response variables, or independent or dependent variables. So we can say for one unit increase in x, y increases by a certain value, the value of b. There are three assumptions underlying the linear regression method. The response variable y has a normal distribution which can be examined using steam and lead plot, histogram, QQ plot. Variability of y should be the same through x. The relationship between x and y must be linear, which can be examined by looking at the scatter plot between x and y. The graph shows the relationship between height and gestational age at birth of 21 children of 5 years of age. The goal is to see if the gestational age at birth is associated with growth. The response variable is height and exploratory variable is age. When these values were analyzed using SPSS, the following values for the intercept, slope, and their standard deviation were calculated and reported. Note that when gestational age was 0, height is 97.9 centimeter. Is this possible? Usually, a regression line should not be extended beyond the range of data where the data come from. And for the clinical and biological data values of x equal to 0, there is no significant value of y. The graph suggests a reasonable linear relationship between the stature and gestational age at birth. Is it because of the value of b that we obtain in these 21 children? We can estimate the confidence interval for b to obtain the range of value that we can be confident contains the true slope beta. A confidence interval at 95% for the slope b is computed using the distribution t, b plus or minus t, sub 0.05, standard error b, where t is the value with n minus 2 degree of freedom in the table of t distribution at 0.05 level. Apply the formula. We are able to calculate the 95% confidence interval for b. Since this interval does not contain 0, we know the true slope of population is not 0. Because lower limit is greater than 0, we can have 95% confidence that the slope is at least 0.052. We have 95% confidence that for every unit increase in gestational age increased the height at least 0.052 centimeters. We can calculate the test hypothesis about the true slope beta. The slope of linear relationship between two variables in the population, the null hypothesis is that the slope in the population is 0. This is implicit when we say that there is no linear relationship between the height and gestational age. The alternative hypothesis is that the slope in the population is not 0. If this is true, we can say that there is linear relationship between the height and gestational age. To test the null hypothesis, we divide the estimate of b with its standard error and compare the result in the t distribution with n-2 degree of freedom. In this example, b is equal to 0.215, ESB is equal to 0.0781, Now, referring to the table of t distribution with n minus 2 is equal to 21 minus 2, which is 19 degree of freedom, the p-value is 0.01 less than p less than 0.02. So what do we conclude from this result? We reject the null hypothesis and say that there is evidence that the slope of the relationship between the stature and gestational age in the population is not zero. Evaluation of a regression analysis involving the comparison of the variance of residual and the variation in the data explained by the regression line, which can be displayed in a table of ANOVA. You should find this look familiar to you. In regression analysis, the total sum of score is equal to the sum of score due to regressions and the sum of score due to error. The sum of scores show how much of variation is explained by the regression line and how much is explained by the residuals. The approach of variation analysis is to compare two sources of variation, regression and residuals, to better explain the variation in the response variables. To do this, we use a test to compare the change in regression and residual variation known as the F-test. The reason for using an F-test is that the ratio of two variants has a sampling distribution known as the distribution of F. The sum of score due to the regression line has a degree of freedom. The sum of score due to residual variance, unexplained, is n minus 2 degree of freedom. To take into account of degree of freedom, we calculate the mean of sum of scores, dividing the sum of score between the degree of freedom. So the mean of the sum of scores is equal to sum of score divided by degree of freedoms. Mean sum of score regression is equal to 45 divided by 1 is equal to 45. Mean of sum score of residual is equal to 4 divided by 2 is equal to 2. We can estimate the value of f as the ratio of mean sum of score, which is f is equal to mean sum of score regression divided by the mean sum score of residual, which is equal to 45 divided by 2 is equal to 22.5. The F-test is based on ANOVA. It's an alternative way to test the null hypothesis beta equal to 0. It is equivalent to the score of t-test on the slope b. The F-test and t-test were to test the null hypothesis that x has no relationship with y. The value of f is referred to the table of f distribution with 1 and n minus 2 degree of freedom to obtain the corresponding value of p, where p is equal to 0.042. The p-value tells us the probability of observing a linear relationship in the sample if the null hypothesis were true and were no relationship in the population. Thus, for a low p-value, we reject the null hypothesis and say that there is a relationship in the population and the regression line traces well in the data. We have worked in almost all terms of an ANOVA table. It remains only to calculate the percentage of total variance explained by the regression line. It is a way of assessing how well a general regression line traces the data. How much of the total variance of a response variable can be explained by the regression line? We call this value R squared, or coefficient of determination, and it is calculated as the ratio of sum of square of regression divided by the total sum of squares. So the formula is R square is equal to the regression sum of score divided by the total sum of scores. In the previous example, R square is equal to 0.8772. It means the regression relationship is very strong. 87.82% of variability in systolic blood pressure can be explained by linear relationship between the weight and the systolic blood pressure. Multiple regression analysis is an extension of simple regression, which allow us to have more than one independent variable. For example, besides weight, we include age, gender, income, activity level in the model to predict systolic blood pressure. Now you have 5 independent variables and are able to see how they play together to affect systolic blood pressure.